So picture this. It's the early days of the internet, and Google has this absolutely insane problem. How in the world do you store a copy of the entire internet? The answer they came up with, the Google File System, or GFS, didn't just solve their problem. It literally laid the foundation for what we now call big data. It changed everything.
I mean, really think about that question. How do you even begin? We're not talking about your vacation photos or some big video files. We're talking about colossal, multi-terabyte data sets, just oceans of information. The file system on your computer would just, fall over and die. So Google had to start from scratch. They had to throw out the rulebook and design a system based on the unique and, frankly, brutal reality of their data. All right, so to build their solution, first they had to really nail down the problem. The design of GFS wasn't some academic exercise. It was forged in the fire of the massive, real-world challenges Google was facing every single day.
Okay, let's be super clear about something. GFS was never, ever meant to run on your laptop. It was built on a wild assumption for the time, that your hardware will fail. Not maybe, but that it will, constantly. So they designed for that. It was also purpose-built for gigantic files and a very specific kind of work, these huge streaming reads and constant appends. Think of a system that's always writing to the end of a giant log file. For Google's massive data crunching jobs, all that mattered was high sustained throughput and rock-solid reliability. Low latency for tiny random reads? Nope. That was a luxury they were more than happy to trade away. So, with those goals burned into their minds, they came up with an architecture that honestly is just beautifully elegant. Let's break down the 3 core pieces of the GFS blueprint. So the first big idea is the chunk. Instead of trying to manage one single, impossibly massive file, GFS just shatters it into these large, fixed-size pieces. You can basically think of these chunks as the fundamental Lego bricks that the whole system is built out of. And when I say large, I mean it. Each chunk is a whopping 64 megabytes. Now, to give you some perspective, a normal file system on your computer uses blocks that are maybe just 4 kilobytes. So why so big? Well, this one decision drastically cuts down on the amount of metadata the system has to keep track of. And trust me, that is a super important detail we're going to come back to. I love this analogy. Think of a GFS cluster like a big orchestra. You've got one conductor, right? Making all the decisions, telling everyone what to do. That's the master. Then you have all the musicians who are actually playing the music, holding the instruments. Those are the hundreds, maybe thousands of ChunkServers. And finally, you've got the audience, making requests to hear the music. Those are the clients. And the rules here are crystal clear. The client is just a bit of code inside an application that needs to read or write data. The ChunkServers are the real workhorses. They're just cheap, off-the-shelf computers that store those 64 megabyte data chunks on their own hard drives. And this is the most important part. The master is the brain. It knows everything about the data, what the file names are, who has permission to access them, which chunks make up which file, but it never, ever touches the actual data itself. That separation is key. Okay, let's zoom in on that conductor, the master. Because having a single master is, without a doubt, the most audacious and you could say controversial part of the whole GFS design. I mean, centralizing everything in one spot, that sounds like a recipe for disaster, right? Exactly. Any engineer worth their salt looks at this for the first time and asks that exact question. If every single request to read or write even a single byte of data has to go through one machine, wouldn't that machine just melt into a puddle under the load? It's a totally fair question. And here is the genius of GFS. It completely sidesteps this problem by making this brilliant distinction between what it calls control flow and data flow. A client only talks to the master once per operation to ask for metadata. It says, hey, where can I find the chunks for this file? The master replies with a list of ChunkServer addresses, and that's it. Its job is done. From that point on, the client talks directly to the ChunkServers to move the actual data. The master is never in the data path. It completely avoids the bottleneck. It's beautiful. This single master design gives it a superpower: global knowledge. Because it's the single source of truth for the entire system, it can make incredibly smart system-wide decisions. It knows the best place to put new data, it knows how to re-replicate chunks when a server inevitably fails, and it knows how to perfectly balance the load across the entire cluster. It keeps all this precious metadata in memory for lightning-fast lookups, and keeps itself safe by writing every change to a replicated log, just in case. Okay, so we've got the theory down, we know the players, we know the basic strategy.
Now let's put it all together and see how data actually gets into and out of the system. Let's see it in motion.
A read operation is just beautifully simple. Step 1, the client application asks the master, hey, I need this part of this file. Where are the chunks? Step 2, the master checks its memory and instantly replies with the addresses of the chunk servers that have a copy. Step 3, the client is smart. It picks the nearest chunk server on the network and asks it for the data directly. Step 4, that chunk server streams the data right back to the client. Notice, the master was totally done after step 2. So efficient.
Okay, now writes are a little more complicated, and that's because you have to make sure that if multiple clients are trying to write to the same file at the same time, they don't corrupt the data. GFS solves this with a clever idea called a chunk lease. For any given chunk, the master just picks one of its replicas and says, okay, for the next 60 seconds, you're the boss. This replica is called the primary, and it's temporarily in charge of deciding the official order of all writes for that chunk.
So here's how a write actually happens. First, the client asks the master magistrate, who's the primary for this chunk? Then, and this is the really cool part, the client pushes the data it wants to write to all of the replicas. The data just sits there in a temporary buffer. It's not actually written yet. Once all the replicas have the data, the client sends a tiny control command to just the primary. The primary then says, okay, this is write number 101, applies the write to its own copy, and then tells all the other secondary replicas, hey, apply write number 101 now. This makes sure every single copy of the chunk is changed in the exact same order, keeping everything consistent.
So as you can probably tell, GFS is a system built on some very deliberate and sometimes pretty extreme design choices. And in engineering, every single one of those choices comes with a specific set of trade-offs. And maybe the biggest trade-off they made was on consistency. See, for its main job, having tons of machines all appending to the same giant log file at once, GFS guarantees that your data will be written atomically at least once. But in certain rare failure scenarios, it doesn't always guarantee that every copy is perfectly byte-for-byte identical, or that a reader will see the absolute latest write the microsecond it happens. It basically pushes some of that consistency problem up to the application itself, and in exchange, it gets that massive throughput and availability.
And this table just lays it all out so perfectly. That single master gives you that godlike global knowledge, which simplifies everything. But yeah, it's also a single point of failure. And its memory ultimately limits how big the whole system can get. Those huge 64 meg chunks, they dramatically reduce the metadata the master has to handle. But if you have a small popular file, you can create a performance hotspot on just one server. At the end of the day, every one of these decisions was a calculated bet, and it was all perfectly tailored to optimize for Google's very specific, massive scale needs.
The ideas that GFS pioneered, separating control and data, designing for failure from day one, optimizing for specific workloads, those ideas are now just baked into the DNA of countless modern distributed systems. But it does leave us with a really fascinating question. In a world that now seems to demand stronger and stronger consistency, is the GFS model of trading some of that consistency for raw, unbelievable scale? Is that still the right bargain to make? That's a debate that's still shaping the future of data right now.